Okay, so I'm going to go fairly quickly through this, so please pause it and go step by step because you have that ability. I'm going to go through taking the rectangular vectors. Here I have 3 rectangular vectors. I don't have them written in IJ format, they're written in the component format. But regardless, if I want to add these 3 rectangular vectors together to get the resultant, one way of doing it is take all the x's, take all the y's, and add them up. This r sub x and r sub y is just the x component of the resultant vector, the y component of the resultant vector. That's one way of doing it. And you come up with a -6 and 17. And that's the coordinates of a point. That's a point at the end of the vector where the vector is pointing. However you want to think about it. But to add 3 vectors, if they're in rectangular form, you add the x's, you add the y's. Now if I want to change it to polar form, I have to find the magnitude, which is not a big deal. You have to usually find magnitude of the vectors anyway, and the angle. So magnitude, here's another way of writing magnitude. One I do in class, I put the 2 verticals on each side. It doesn't matter. You'll see different notations for it. But the magnitude of r is equal to the radius of the polar vector. And in here you notice I do not put the negatives. They're irrelevant for this purpose. They're more likely to cause an error than anything else. And voila, I get the radius of the polar vector. I get the magnitude of r is approximately 18.03. Now we have to find a direction. And you look at your components of your resultant vector, and this is telling me go -6 left and up 17. Well, that's telling you you are in the second quadrant. And the angle I actually want is this angle from 0 to that terminal side. The angle we're going to find is this one. So if I look at how I have this drawn, this distance is 6. I know it's -6, but I don't care. The distance itself is 6. The distance up is 17. I want that angle. What we always do is tan inverse. Here, this is an older notation I'm using where it's in absolute values. To remind you, you don't put negatives in. You just don't put the negatives in. You think about where it's at. In this case, 17 over 6. And I get a little equals in here, or space in there. There we go. I get the angle 70.56. This angle is the 70.56. The angle I want is that one. So I have to go 180 minus 70.56, which is 109.44 degrees. So my polar vector is 18.03 at an angle of 109.44 degrees. I did not talk about equilibrium vectors yet in class. The equilibrium vector is pointing in the opposite direction. So if I go back to my picture, equilibrium vector, the resultant vector is trying to pull this point this way. It is a result of all 3 of these vectors acting on the point. The equilibrium vector, just picture one 180 degrees opposite, with the same magnitude, is going to hold it in check. That's what I'd have to use to hold it in check. Rectangular is very easy. You just switch your signs of the x's and the y's. Polar, the easiest way to think about it is if you know this angle, add 180 to it. If you're over here, you'd subtract 180. Basically, you are going to either add or subtract 180, but you do have to end up in from 0 to 360 degrees. So sometimes you have to think about it a little bit. Not really the purpose of this video. All right, how do you add polar vectors? Well, first thing you're going to do is find the xy components of each vector. And the component, this is called the component method. And I advocate the component method is the best, most efficient way of doing it. People will show you other ways, whatever. This way always, always works. So if I give you 3 vectors, in this case they're polars, so I'm saying the radius is representing a force in pounds on each, and you have a directed angle that the force is pulling on. I want to find the resultant by adding these together. Well, I can't just add the degrees and the r's. That makes no sense. So I'm going to take each vector and find its components. Now you might want to pause it for a second and scroll back up. I'm going to scroll back up to these formulas right here. Y is equal to r sine theta. And this should be x, that fixed right now, is equal to r cosine theta. Save it so I don't forget. So when I come down here to the formula, I'm taking r times cosine. That's going to give me my x, and that's why I'm writing it in I component notation. 67 sine 48 is going to give me the y, and that's why I'm writing it in j. This is another notation you're going to see in engineering and other fields. So vector 1 is being changed from a polar to this rectangular. The number in front of the I represents my x component. The number in front of the j represents my y component. And if I do that for each of them, check my work, I have my components, and now I simply add up my x's like I did before, add up my y's like I did before, and I end up with my resultant vector is 91.61i plus 10.73j. Polar form, okay, I'm finding the magnitude, I'm finding my reference angle. Notice there's no negatives on this one. I wouldn't put them in here anyway. My angle is 6.68 degrees, and since this vector is in the first quadrant, this would be our angle. And yeah, no picture on that one. So you just got a picture. It's over saying go right that far, up that far, or with this much force and that much force, however you're interpreting the magnitudes of the components. Here I have another one for practice. I made up a negative 12i minus HA. I want to change that to polar form. So first thing you figure out is what quadrant it's in. Well, it's in the third quadrant. This distance is 8, this distance is 12. I don't care about the coordinate. I'm just saying the distance is 12, this distance is 8. We're going to find this angle, and once I find that angle, we have to do something with it. Remember, there's 180 to there. So in this case, I'd take 180 and add that. So I find the magnitude. Again, I'm not using a negatives there. I do my tan inverse. Again, I'm not using a negatives there. I get my reference angle. And I remember, oh, that's this angle. I have to go 180 plus that. Okay, so that's a process you're always going to follow. So practice, practice, practice.